So far, you've learned how to track the maximum power point of a solar panel indirectly through various methods. In this video, we will discuss the first direct technique for MPPT, which is the Perturb and Observe technique. You will learn how this technique works, and we will look into the drawbacks associated with the Perturb and Observe method. So let's start with a quick recap. Just like with all other techniques, the goal is to find the voltage at which the solar panel outputs the most power, VMPP. Once we find VMPP, we will use some power electronics to make sure that this voltage is applied to our solar panel. This can be done in different ways. We can divide all techniques into two different categories: indirect and direct. We already went over some indirect methods used. In this video, we will focus on a direct method known as the Perturb and Observe technique. The logic behind this technique is quite simple and straightforward. Basically, the MPPT continuously makes incremental changes to the voltage and monitors changes in power. If the change in voltage increases power output of the solar panel, the next perturbation will be in the same direction. If the change in voltage decreases the power output of the solar panel, then the next perturbation will be in the opposite direction. This table shows all the possibilities. You can see that if the prior perturbation was positive and the change in power was positive, then the next perturbation will be positive. However, if the change in power was negative, then the next perturbation will be a negative change in voltage. Let's take a look at how this would work. It should be noted that the perturbations used here are exaggerated. Usually, the perturbations would be much smaller, but here we have a normal power voltage or PV curve of a solar cell. Let's assume we are operating at the red dot and we want to find the maximum power point. Well, our first perturbation would be random since we don't have any information. So let's just choose a positive voltage perturbation to start. Now, the voltage has shifted positively and the power has gone up. Therefore, the next perturbation should also be positive. Again, we have a positive perturbation with a positive change in power. This means we will again increase the voltage. Now you see that the increase in voltage has resulted in a decrease in power. This means we will reverse our voltage perturbations and decrease our voltage. A slight increase in power is observed, so we will further decrease the voltage. Now you see that after this perturbation, we end up with a decrease in power, so we will reverse directions again and increase our voltage in the next move. Now you can see that we actually reached the maximum power point. However, the system doesn't really know that we have reached the maximum power point, so it will continue to make moves. You can imagine the result will look something like this. The system will constantly make perturbations moving around the power point. One thing you may have noticed in our example is that the voltage perturbations were not all the same size. This can be programmed into the logic in a few different ways. In some cases, moves in the same direction will be large, while moves in opposite directions will always be small. More advanced techniques can store where the power maximum was and only have small moves once a global maximum is reached. Here you can see the block diagram used for the Perturb and Observe technique. As inputs, it needs the instantaneous voltage and current of the solar cell. It also needs to store the voltage and current before the previous perturbation. Using that, it can calculate whether the current perturbation was positive or negative, and therefore it can decide which direction the next perturbation should be. The logic can also consist of other, more advanced aspects, such as the size of the perturbations depending on some other data stored in memory. So now you should understand how Perturb and Observe works. Basically, this technique literally scans and keeps making changes to stay around the maximum power point. However, there are some problems with this technique that could result in unideal perturbations. One such problem occurs when a radiance changes during a perturbation. Here we see a similar situation to the one we showed earlier in the video. Let's assume that first a positive perturbation is made, increasing the power. Then, before the next perturbation, the irradiance drops due to light cloud cover. Now, PV curve has changed. However, the system has no knowledge of this, so it would make a positive voltage move just as normal and records a drop in power. Naturally, the system will now assume that the maximum power point is to the left of the current voltage, and so it will move in that direction. The system will eventually correct itself, but these changes in radiance are frequent enough it could result in a PV system operating far from the maximum power point for a significant amount of time. However, even with this drawback, the perturb and observe technique usually results in better output than using indirect methods discussed in the previous video. As a final note, before I conclude this video, it's good to know that there are multiple ways to use the perturb and observe technique. In the classic approach, perturbations are generally constant, a value like 0.37% of the VOC of a panel could be used. However, a 3-point comparison is also sometimes used. In this version of the algorithm, the system checks a perturbation in both directions and then observes which perturbation has the greater power output. While a bit slower, this method is more robust once the system is closer to the maximum power point. Now you're familiar with the first direct MPPT method, the perturb and observe technique. You understand how the technique works in the classic sense, as well as some advanced aspects to it. Furthermore, you understand the potential drawbacks to the method. This is the most simple direct MPPT method. Next, we will look into the incremental conductance method.